I want to show you some typical errors, or one typical error that occurs very often in this kind of a proof. Okay. And notice here that I started with my assumption P of n and I somehow massaged it to P of n plus 1. Okay. Now, a lot of people, and this is an error, start with, the claim they're trying to prove. And their logic goes like this. Let's see what happens if, P of n plus 1 is true. So let me assert P of n plus 1 to be true. So let me assert this. So let's see what happens if, let's see what happens if I assert P of n plus 1. Okay, so what am I asserting? I'm claiming as if it's true, the sum up to n plus 1, 2 plus 3 plus up to plus n plus 1 plus n plus 1. Let's see what happens if I assert that this is equal to what I want. Is equal to 1/2 n plus 1 n plus 2. Okay, then, let me subtract n plus 1 from both sides. So that's perfectly legitimate. So 1 plus 2 plus 3 plus all the way up to plus n. So I've subtracted n plus 1 from here. That should equal 1/2 n plus 1 n plus 2 minus n plus 1. Okay, and now let's do some basic algebra. That's equal to 1/2 n plus 1. So I'll factor out 1/2 n plus 1. Okay, and now I'm going to get in here n plus 2. So that's this term. Okay, and I'm going to get a minus 2. So the minus 2 cancels out with this 2. So 1/2 n plus 1 times minus 2 gives me minus n plus 1. So that's basic algebra. And now let me simplify. N plus 2 minus 2 is n. So this is 1/2 n plus 1. And I have such a large amount of relief here because look, by sort of asserting where I want to go is true, I have managed to derive something which I know is true because I assumed it's true. So nothing bad happened. Okay. This is known to be true, so nothing bad happened. And so therefore that means that where I started must be true, and that's the end of the proof. Therefore I have proved P of n plus 1. And, I'm going to emphasize that that is wrong. Okay. So, wrong. Okay. Never do that. This is the sure way to get a 0 on an induction proof. Okay. You can never assert what you want to prove as though it's true. That's what you have to prove. Okay. And in this flawed proof, what you have done is you have asserted what you want to prove as true, and you have proved what you already know to be true by assumption. So you've accomplished nothing. Okay. Now, I want to emphasize, you can never assert what you want to be true and then derive something that you know to be true and then, give a sigh of relief and say, oh, I'm great. I didn't get somewhere that's nonsense. So where I started must be true. Okay. And I want to emphasize this, and I want to tell you that, this method of proving the implication is just flat wrong. And I want to show you an example which is of the same type. And when I show you this example, you'll have no doubt that it's wrong. Okay. So I'm going to prove to you that 4 equals 7. Okay. That's what I want to prove. Okay. So, 4 equals 7. That's what I want to prove. Okay. So, now I'm going to do all kinds of cool stuff. Okay. I'm going to do stuff that I'm allowed to do. Forget about the fact that I'm not allowed to write this down. I'm going to do cool stuff that I'm allowed to do. So, if 4 equals 7, then 7 equals 4. Because we learned, that if A equals B, then B equals A. Equality is what's called, symmetric. Okay. Well, but then we also learned that if you have two equations, you can add. So this plus this equals that plus that. Look, so 11, so 7 plus 4, adding is equal to 4 plus 7. Adding. So this means that 11 equals 11. Okay, subtracting, and then I come to 11 equals 11 and I say, oh, wow, sigh of relief. I've derived something that I know is true. Just like here, I derived something that I know is true. So therefore, I must have started somewhere true. False! False, false, false! Okay. You cannot start where you want to prove. Okay. And then do real stuff valid stuff and end up at something that's known to be true and then therefore claim that where you started is true. It certainly cannot be done here and it cannot be done here. So don't do it. Okay, bad proof. Now, I want to, illustrate the problem with induction. Okay. And it's a real problem. And maybe you've noticed this problem with induction. Okay. So the problem with induction. Okay, you might have noticed it. And, let's just imagine, that I'm not the great Gauss, and I didn't come up with this formula 1/2 n plus 1. Okay. So the question is, where did I get that formula from? Okay. So where did the formula come from? And this is the sort of drawback of induction. Okay. Induction is not a derivation. Okay. So where did the formula 1 plus 2 plus up to plus n equals 1/2 n plus 1? Where did it come from? Okay. Did I just get it out of nowhere? Well, no. I had the great Gauss who showed me that method of heuristically deriving that formula. Induction is not a derivation. Okay. It's a proof of this formula, and it can only go once you have something to prove, once you have the formula to prove. Okay. But where did the formula come from? Well, you have to somehow get the formula, okay, and then you can prove it with induction. So that is the drawback with induction. It doesn't give me the formula. It gives me the method to prove the formula. So then where do I get the formula from? Well, somehow I must get the formula. So in some sense, I won't be able to prove an untrue formula. So in some sense, I must get a formula that's true. Okay. So it's kind of circular. I must get a formula that's true, and then I'm going to use induction to prove it's true. Circular. Problem. Okay. So, the fundamental thing about induction is that it gives you a method to prove something. Okay. It doesn't give you the thing, the formula, or whatever it is that you are to prove. Okay. But all is not lost, because what you can do is come up with a guess. And once you have a guess, you can use induction to prove that the guess is true. Okay, so you can prove the guess with induction. So that's where typically induction is used, is that, we get a guess, but a guess is not a proof. And then we use induction to prove the guess. And how do you get the guess? Tinkering! Okay, so to get a guess to prove by induction, you tinker. Very important. And now to see how that would work in a situation where, it's not obvious what a formula is, as in, using techniques, for example, that were used by the great Gauss, try to guess a formula for the sum of the squares. So S is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... up to n squared. Okay. Now there's no immediate formula for this, so we have to make an educated guess. Okay. And the book illustrates a method called the method of differences, which allows us to get, is a reasonable method for getting guesses for formulas like this. That guess is not a proof. Okay. And then once you have the guess, you can use induction to prove it. So I encourage you to go through the entire process of sort of guessing the formula by tinkering. So you try S for n equals 1, n equals 2, and so on and so forth. Try to come up with a guess. And then induction can be used to prove the guess is true. Okay. So the power of induction is not in getting you the formula, it's in proving the formula is true. You have to guess to get the formula, and in order to get a reasonable guess that has a high chance of being true, you have to tinker. Okay.